so what are we up to here? Right, we're learning about springs. And what you're trying to do is to determine, so the aim is all very clearly given on the sheet of paper. So follow that word by word. Again, don't copy this entire thing as your work. Just, it's only for reference. You can always add a lot more than what is there. What is the aim of this experiment? To investigate the properties of a spring and determine the spring constant by two methods. One is the extension method and the other an oscillation method. The extension method is what is on this page, and on the opposite page it's going to be the oscillation method. So by two methods. The materials required, we need a stand, a clamp. Now these are kind of ready-made stand and clamp and everything like that. So you can see that it is ready-made stand and clamp. The spring is already there, everything is here. So if you don't have that, and suppose you do have a spring that you need to investigate, you can use a normal stand, a normal meter stick, and so on. Okay, so you can always work with it. That's the ready-made thing. Stand, clamp, spring, weight hanger. This is a weight hanger, and then the weights, which I have a couple of weights here, a scale and a stopwatch. So you all have stopwatches, right? So what do we have to know about springs is that every spring, when applied a force, it stretches. When you apply a force on a spring, it stretches. And the force that you apply and the stretching is directly proportional to each other. So the force is directly proportional to the extension. The force is directly proportional to the extension. Force is directly proportional to extension. That means if you plot a graph of force and extension, it's supposed to be a straight line, starting from the origin. This simply says when you don't apply any force, no stretching. You apply more force, more stretching. But of course, the spring has its own limits. You can't just keep going on and on and on. Beyond a certain extension, the spring can get damaged. Right? Any spring will, once it crosses the limits of anything, if you cross the limits of anything, it's going to be damaged. So once you cross the limits of extension, this is okay. It's coming back to normal. But if you cross it too much, then it won't come back. It will be permanently deformed. So F is proportional to X only before you reach those kind of limits. Okay, so within proportional limits, F is proportional to X. And so F is equal to Kx, where K is a constant for the spring. And the K is F over X. Whatever force you apply divided by the extension, that is a K. And the unit of K is Newton per meter. Newton per meter, that's the unit of K. And every spring has a different K. For example, if it's a tough spring, the spring can go like this. What does it mean? That means in spite of the fact that you put a lot of force, it only stretches by this much. Okay. Or if you take a slinky, it can be like this. The tiniest amount of force will make it grow a lot. So every spring has a different K. If it is like this, then it's going to be tough spring. If it's like this, a medium. And this is a small K. K kind of tells you how tough a spring is. Now you do have springs in there. We have springs in the car, right? Trucks. We have springs under the trucks. We have springs under the trains. Now, those are all top springs. Even after loading it by tons, it only like goes down by a little bit. And springs are always made of steel because steel is, which is more elastic, rubber or steel? Which is more elastic, rubber or steel? Now when I ask such questions, always go for the opposite answer. What do you think? Right? What is it? It is steel. Steel is more elastic than rubber. People mistake the words elastic. The word elastic is totally different from flexible. Rubber is stretchable, yeah. Rubber stretches a lot. That doesn't make it elastic. What's the meaning of elasticity? Elasticity means how readily it returns back to its original shape and size. That is elasticity. But people kind of always, think that elastic means stretching, and so rubber is more elastic. In fact, rubber is the worst in elasticity. Rubber does not like to return back quickly. Rubber does not like to return back very quickly. The response is very poor. Rubber is retarded. Rubber is retarded, which means what? Slow to respond. Retarded means like, don't go into extremes. Like retard means like pull back. Yeah? So if someone is slow in thinking, what will happen is reflex time is going to be definitely lost, right? If this marker is going to fall from my hands, I'll just like quickly spring him and catch it. That's reflex. If you're drunk, you're not going to be able to do that. That thing falls, and after that you're like, oh, yeah. Basically, if you're drunk, you're drunk. So, because our response is definitely slower than normal. That's why it's bad to drive and drink and drive, right? Because once you drink and drive, and your response is definitely going to be slowed down. So you are not going to be able to correct your procedure in time, and you can actually go off the road. The other day I was like driving on 71. As soon as I got on 71 from Gene Snyder, someone just like brushed my car and went. But I was like, ooh, I'm just merging. And I got onto the last lane. And this car literally went so close to my door. I was like, and I moved away from there, and then the car went. And then I was like, the car was not driving right. Like one wheel is on this track and one wheel is on this track. So like halfway. And then suddenly the car will sway and go all the way to the end outside the road. And then after that come back again. And almost go off the road. And I was like, I took my phone and I started recording it. I started recording the whole thing as I was driving. And I was going behind, but I didn't want to catch up with it. And some people are getting angry and they just went, like they're angry because I was carefully driving behind that person. And I knew that something is going to happen. I think that video is posted on YouTube, on my thing. So what happened finally was like, Gene Snyder, from Gene Snyder to Waterson, that space, that's when I recorded it. And then this car, at one point, it actually went off onto the grass, the slopey grass. It literally went off the grass and like somehow like climbed back again. Last moment, I thought, oh my God. I was like, literally, it's going to happen, But who can stop it? He's going really fast too. And then swaying to the other side, and like almost like hitting the other cars, and going this way and that way. And I was like, something is going to happen, and I'm coming to pieces. So I was like, I'm supposed to go this way. And as soon as the Waterson was getting close, that person kept to the last lane, and the turn, right? And for his bad luck, there was a lot of traffic over there held up. And as I was watching, he just went plowing into the cars and hitting the cars. At least 3-4 cars were almost like crashing into each other. And I took that and I had to take my right turn and came on. Yeah, so I'm pretty sure that was some kind of impairment. Now, if it was a person who was sleepy, now when he went onto the grass, he would have definitely stopped over there somewhere, right? Definitely that is not sleep. It was something awkward. And also fast. Not slow driving, fast driving. Anyway, coming back to this, elasticity. The rubber is very slow in response. That is why we use rubber for our tires. Because rubber is a good shock absorber. Why rubber is used as a shock absorber? Because rubber can get squished and won't return back quickly. Now think of driving your car with steel tires. It will radiate all the shock vibrations right into your steering wheel. Okay? So rubber is actually a very good material for absorbing shock. It won't take anything. Nothing's going to happen. Yeah, so the response is very good. Steel is very good. That is why we use steel for springs. Makes sense? So which is more elastic, steel or rubber? Of course, it's steel. Rubber is not elastic. It is flexible, but it's not elastic. In English, we use a lot of words wrongly. Wrong usage. Okay? And that is very common. Very, very, very common. What is this? Battery? This is not a battery. This is not a battery. This is a cell. Who calls it a cell, right? Now, if I go to Walmart and say, tell me where the cells are kept, they'll be like, what do you mean the cells? Now, this is an electric cell. It's not a battery. Now, what is battery? That is important. Battery is a group noun, group name. Have you heard battery of soldiers? No? Battery of soldiers. Flock of birds. So there are lots of birds flying. You say, there goes a flock of birds. Now, can you just, if you see one bird flying, can you just say, that's a flock? That's not a flock, that's a bird. So this is actually a cell. Now, when you use multiple cells together, it becomes battery of cells. Make sense? So when they initially made all those transistorized radios and flashlights and all that, more than one of these is required. So they said radio operated by a battery of cells. Flashlight operated by a battery of cells. They got tired of saying battery of cells, they chopped it to battery. So they said battery operated flashlight, battery operated. Now, it's a wrong usage, but they just started using it. And finally they started getting called as a battery, which is wrong. This is a cell. Make sense? Like that, there are a lot of mistakes, I mean, like wrong usages, we don't use them. But again, knowing that this is not a battery, I definitely will go to Walmart and say, where are the batteries kept? Which isn't only right, because batteries of cells, where are they kept? Yeah. This is one of the other. Elastic, which is more elastic, steel. Rubber is not. Okay. Now, K is what differentiates one spring from the other spring. So you have a couple of springs over there. Now, if you have to do the lab on these springs, they all will have different Ks. So everyone's answer is going to be different. It's going to be different. But we're going to work with, and I'm going to work with one. So do you want to work with the other one? I can provide you all the materials. Or you can just watch this and take readings straight away. What do you want? Me do it? Okay. So that is the first part. This is our equation that we're going to use for the first part. And the second part of the is the oscillation method, which is like the pendulum. If I put some weights on it, If I put some weights on it, and if I let it bob, there's a timing. The time period depends on what? Can you see the equation there? The time period is given by 2 pi radical m over k. K is this value. K is how tough the spring is. So what do you think is going to happen to the time if the spring is tough? If the K is big, time will be short. So it will go fast. What do you think is going to happen if the mass is more? Time is going to be more. So you saw that. Look at this time. Mass is less, time is less. And look at this time. Mass is more, time is more. Right? The same with your cars. Your car springs. If you're the only person without anything in the car, and then you go over a speed breaker, your car will be a quick response, but quick. The oscillation will be quick. So imagine there are 5 people sitting in your car. It's a heavy car. Now you go over the same speed breaker, it will go like, it goes slow. But the timing will be more. The timing depends on what mass you put in. So that is the oscillation part of it. So we're not going to use that equation as it is. We're going to simplify this equation and square both sides. We get 4 pi squared m over k, and then we make the k the subject of the equation, so we get 4 pi squared m over t squared. So that is going to be our equation for our oscillation method, and that is our equation for our extension method. 2 methods. And for the extension method, we're going to draw a graph with x. Just kind of graph. We're going to draw a graph, and from the graph we get the slope, which is the k. The slope of the graph is k. Alright. The procedure is what? Clamp the spring to the stand. It's already done. Prepare the spring with the hook and dead weight. Now what is a dead weight? Dead weight. So spring is spaced apart. Can you see the spring right now? And most of the springs that you have, there's no space at all. It's like stuck together. So if I put some weight here, see, I'm putting some weight. This is 10 grams. I'm putting 10 grams and I don't see anything happening. It is still tucked in. So when I put some weight, it is supposed to show some stretch. It is not showing any stretch. That's because the spring is already like compressed windings and is not ready to exhibit this. So in order to prepare the spring to make our experiment successful, we need to space those springs apart. And to space it apart, we need some weight to put in over there. So I'm going to put in some weight. I'm going to put in some weight. This will be our, so this is a 50 grams. So 50 grams. So when I put 50 grams, it is stretched. Now it is ready for the experiment. So this is called the dead weight. What you see right now is called the dead weight. That is not going to be in our table. So what am I going to write for the mass of this weight in kilograms? You put 0. No. Just put M. Just put M. So the first column. Mass in kilograms, you put just M. Okay? And that's our dead weight. And when it is M, I need to know how much is the reading, because I need to get the readings. So I have attached a little pointer to serve it's easier for me to kind of use the pointer and I can read it from there. So I kept the pointer there, and let me read. .5 centimeters. So what is our next column? Reading in centimeters. Can you just write 3.5 centimeters there? So that's what is reading. Okay. So the reading, I'm not interested in what is happening, but just reading is 3.5. That's what I see. Now, I need to know how much it can take maximum, because I don't want to load it too much. So I just want to test and see how much it goes. Now, this is let's 200 grams. Yeah, that is 200 grams. Let's see what happens if I put 200 grams. It's going there. And I put 300 grams. It's going there. That's good enough. So 300 grams, it's able to take 300 grams perfectly fine. So what I'm going to do is I'm going to experiment installments of 50 grams. I'm going to work in installments of 50 grams and find out the readings. So we change. Now to show me 3.6. Can you write it as 3.6? 3.6 the start. Now I'm putting 50 grams onto it. So when I put 50 grams onto it, it sinks a little bit. And my reading is 5.1. So what are you going to write here? In the second column, right here, you put m plus 0.050 in kilograms. 50 grams is 0.050. So right here, m plus 0.050 in kilograms. And the reading, what was it, 3.6 first, and this is 5.1, right? So right in centimeters. And let's complete it that way. I'm going to now put 100, total 100 grams. So what I'm going to do is, I'm going to remove the 50 and put 100 instead. And the reading is 6.6. 6.6. So what is right here? M plus 0.100 and 6.6. Now I'm going to add one more 50. So it becomes M plus 0.150. And this reading is going to make sure that it's not oscillating as you take the readings. 8.2. And the next one, I'm going to take this 50 grams out and I put 100 grams in. So the total reading is M plus 0.200. And the reading is 9.9. And the last reading I need 1, 2, 3, 4, 5. One more reading. I put 50 grams more. So this reading is M plus 0.250. And the reading is We got our readings. That's what we needed. Now, how do you fill the column of extension? Since we have not started the experiment here yet, extension is 0. And when you put 0.050, extension is the difference from here to here. How much is the difference from there to there? 1.5 centimeters. For the next one, the difference from here to here. But that's going to be a base number. And then from there, the difference. How much is it? 3.0. And for the next one, it's going to be from here to here. How much? 4.6. And the next one is from here to here. 6.3. And the last one from here to here. 7.8. Okay. That is this column. And the next column is convert them to meters. Convert them to meters. So this is going to be 0, and that's going to be 0.015. We're going to divide this by 100 to change it to meters. From centimeters to meters, you divide by 100. And the last column tells you what is the force that caused the extinction. What amount of force caused the extinction? The force that caused the extinction is the weight. The weight, what's the formula for weight? What's the formula for weight? Mass times gravity. Mass times gravity. So for the first one, you put 0 because our dead weight is considered to be void. Now what is the mass over here that caused the extinction? 0.050. So what is the weight then? So 0.050 times 9.8. That's going to be our answer there. How much is that? 0.49 seems right. Newtons. Yeah, 0.49. Now, what's the next one? Next one is cost by 100 grams. So 100 grams times 9.8. So basically 0.100 times 9.8, and that is 0.98. Like that, you build that column. And the next one is 0.150 times 9.8. And what is it? 1.47. The next one is 0.200 times 9.8. And that's 1.96. And the next one is 0.250 times 9.8, which is 2.45. So you're done. That's it. Now we're going to plot the graph. So because we need to draw force extension graph. So let's go to the graph now. So we're going to work with the graph. What's going to be our y-axis? Force. So that's going to be the y-axis. And which ones are x-axis? Extension in meters. And this is going to be our x-axis. So on the Excel, what is going to be plotted? Is it out of focus or what? Looks like. It is? Is it out of focus? Yes, right. Looks like focus. Oh, I'll erase the stuff, but it is definitely out of focus. Huh? I don't think so. That's why I checked. I don't think there's a remote option. I think you need to physically do it from there. Yeah, it is. Yeah, there is. Pretty sure there is some. Don't like climbing. It's good enough? I think so. It's definitely good. Okay. Yes. So this is going to be our x variable, which will go into column A. This will go into column B. So let me. Alright, I'm going to read the numbers in. Column A, 0, 0.015. Point 030. 0.046. 0.063. And 0.078. And then our y variables are 0, 0.49, 0.98, 1.47, 1.96, 2.45. You got it? Then you know what to do next. Select it. Click on Insert, Charts, Scatter. There is our graph. add axis titles and chart titles, put over there extension method. And the axis titles. Course. Images. Extension. Images. And then we need to draw the best line. So right click on any of the dots, add trend line, and then go down here and click on display equation on chart. So that is our equation. That is our equation. So I get y equal to 31.168x plus 0.0198. So that 0.0198 is supposed to be the force error. How much errors come out in forces? And that can happen because of the weight itself. This weight is probably worn out. You know, it's not necessarily exactly what is printed. If it says 50 gram, it need not be 50. It can be slightly off. And the other error is the precision of this thing. The precision of the scale is only a millimeter, so I do round up and down, right? You know, some of the readings, like 9.9, it appeared like 9.8. I just chose to have it as 9.9, so that's how. So errors can come in like that, and that is why we have this number. So what is the slope? 31.2. 31.2 is the slope. And the slope is K. So K is 31.2 Newton per meter. That is the answer. By what method? By extension method. So we have done the extension method. We have done the extension method. Now we're moving on to the oscillation method. For the oscillation method, there is no such thing as dead weight. Because whatever is hanging on the spring will have to be taken into account. So I need to know how much it weighs. I need to know how much the stand weighs. I mean, like the hanger weighs. 16.8 grams. 16.8 grams. Just a minute. So keep that in mind. The mass of the hanger is 16.8 grams. So for the extension, for the oscillation method, what we're going to do is this. We need to put some weights over here. including this. Everything that's hanging on the spring is to be counted for. So I already weighed this, so I know that. And I'm going to put 4 grams. And I'm going to toss it up and down. And you're going to do the timing. Go ahead, start the stopwatch. And you know how to do the timing? As soon as it crosses, as soon as the pointer crosses the mean position, so that's a mean position. That's a mean position. That one. So as soon as it crosses there, that's when you start the stopwatch and stop the stopwatch. So let's do the timing. So exactly how you start the stopwatch, like count 0 when you start the stopwatch. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want answers from everything. Can you display your time? Find the time period. Find the time. How will you do it? Do you start at 0? Try it again. Everybody else in here with that? 5.47. I got 5.20. But how you do the timing? It's only count it loud. As soon as it goes down in the middle, that's when I'm going to count it as 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.28. Try again. 5.21. Good. Take that. I'm trying again. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.28. I got 5.28 2 times. Again, I'm trying. So we are around there. So you can take those numbers 5.22, 5.28, 5.28, and that will be written down as 3 timings. And what's the mass that you're going to write there? It's 200 grams plus the 16 grams, 16.8 grams. Together it is 0.2168. 200 and then 16.8. So 216.8. Change it to meters. 0.2168 kilograms. Of course, in terms of sig figs, there's no point in keeping the 8, so it's good to call it 17 grams. So you do one thing. On the mass, don't write it as 0.2168 instead of write 0.217. 0.217 kilograms. And we got the 3 timings, 5.28, 5.28, 5.22. Take the average of all these 3. 5.24. 5.28, 5.28, 5.22. So the average of all these 3. 12, 4. So 5.26 is what you should get.
I think I have my 3 numbers different. Sorry.
Okay. 5.26 is the time for 10 oscillations. And then the next column says time period. So what do you write for the time period? 0.526. So your table goes like this. The table goes like that. Mass in kilograms. The first mass that I put there is 0.217 kilograms, and the times for 10 oscillations in seconds. You got 5.28, 5.28, and 5.22 seconds, and the average time period, sorry, average time for 10 oscillations is 5.26 seconds. And then you have the time period, which is in seconds, 0.526. And then you're supposed to find the K. I gave you the equation already. What is K? K is equal to 4 pi squared mass over 2 squared. So for this, that's what you do. So what do you do the calculation? 4 pi squared mass. What's the mass here? 0.217 divided by what's the time? 0.526 squared. Can you do that calculation? Tell me what answer you get, and that's what you put here. Do that calculation and tell me what you get. It's supposed to be 0.2168. I rounded to 0.216. You know, 16.8 is like 17 grams. When you're adding 16.8 with 200 grams, you're just rounding it up for SIGFIX. 16 point? What did I say there? I don't know. Did I say 16 point?
That was for the hanger.
Yeah, how much was it? Yeah, 16.8 it was, yeah. 16.8 is what I told you. Yeah, that's correct. Okay. Okay. What's the answer? You do all this, what do you get? How much? 30.927. That's fine. 30.9. See, this is our value. Remember, this is what we got by extension method, and that's the answer that you're expecting to get. So you're good. Pretty close. We are expecting to get the same K because we're using still the same spring. So the K is supposed to be somewhere here. We don't know exactly where. Is this correct or that's correct? But we're going to take averages. So what do you do next? Do for one more mass. So we already have the 200 grams hanging there. I'm just going to add another 100 grams. So now it is totally 317 grams. So it will be 0.317. And let's do the time. Come on. How much? 3 point. It's 6 point. Yeah, I got 6.39. Let's try again. 6.39 is what I got first time. Let me try again. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6.38. both my reading. Let me try one more time. 6.41. So I'll go with that. So 6.38, 6.39, 6.41. Take the averages. So 6.39 is it? Yeah. And then so the 0.639. And then use that equation once again. 4 pi squared times 0.317 over 0.639 squared. How much?
30.7.
30.7. And then what you do next is to take the average of those two, and that's what's going to go into that column. So what is the average of this? Average of 30.9 and 30.7 is 30.8 Newton per meter. So we got the K by oscillation method, we got the K by extension method. And they both kind of agreeing with each other. So as far as calculations are concerned, in the calculations column, in the calculations, you have to show your graph for the extension method, and also just write down the slope from the graph right there, which is 31.2 Newton per meter. And the oscillation method, just take the average of those two, which is basically 30.8, and put it down there as your final answer. Oscillation method, K is 30.8 Newton per meter. And now, as far as precautions are concerned, you know what all we did. When we're doing the first extension method, we took care of the dead weight thing. That's important. So that the spring is capable of stretching according to forces. And we also for the oscillation method, make sure the hanger is included. And the other one is the timing. Make sure the timing is like, for 10 oscillations starting from 0. And repeat the oscillations 3 times at least for better accuracy. And you can also mention about the pointer that is attached to the bottom of the hanger for our reference to take the readings. Extension method, it is very difficult to see the bottom of the hanger, but with the pointer, you can see the pointer that is attached to the hanger, right? The pointer actually makes it easier to read where it is. And that is basically what precautions are. In conclusions, write your understanding about what you learned through this experiment, and it's a beautiful experiment where you learn about springs. Because we are using springs everywhere. Even in your pen, you have springs. since already we have drawn a graph on this one, there's no need to do the graph. That's why we're just doing two masses, and that's taking the average. If we want to really do it the graphical way, we keep doing this for 5 different masses, and then we will plot a graph of m versus t squared, mass against t squared, and then get the slope and then use that slope. You can do it, but you don't have to do it. Because you already know that it's coming so close. Look at that. So what we got over there is 31.2, because I trust this more than that. Because that one, there's a lot of source of error that can come because of this. This thing is very rough. With this one, we are taking the time with the precision of 100th of a second, so less likely to make mistakes, unless we personally make mistakes in time. All right, any other questions? We are done in